So we're going to talk about volume by the disk and washer method today. And so the disk and washer method uses rectangles perpendicular to the x-axis or y-axis, the axis that you revolve around. Okay? So say you've got some problem and you're given some curve. Okay, so some f of x curve, and I want to revolve around the x-axis. Okay, then rectangles that are perpendicular to the x-axis look like this, and so they are dx cuts. And so what does it look like to revolve around? Well, if I spin this sucker around, then I'm going to have this mirror image on the lower side, and whenever I spin it around, it creates these little discs, okay? And so the idea here is we're going to find the volume of each of these little discs and add them up from A to B. So perpendicular is how I remember the disk method. So the disk and washer method is perpendicular, so I think it's kind of goofy, but I think perpendicular. Okay, so that's kind of how I go about remembering how my rectangles are perpendicular to the axis. Remember, perpendicular means a right angle, perpendicular to the axis that you're revolving around. All right. So we have a problem where we want to find the volume of a solid created by revolving the region bounded by the lines of the curve about the x-axis. Okay, so let's draw it up. So I want to draw this up here. Okay, and I want to have this is y-axis, this is the x-axis. Now, x equal to 0, that's the y-axis. All right, so that's the y-axis, that's x equal to 0. X equal to 2. X equal to 2 here, another vertical line. And then y equals e to the x. This is an exponential function. That's an exponential function. So let me change those colors there. And exponential function passes through the y-axis at 1. Oh, that's not what I wanted. So something like this here. All right. So this is y equals e to the x here. So we pass through at 0, 1 here. And then here it's at 2, e squared. Whatever e squared is, so 2.71 squared, basically, approximately. All right, now what I want to do is I want to revolve this thing about the x-axis. So I'm spinning it about the x-axis. So whenever I use the disk method here, and now the difference between the disk and the washer method, a disk, okay, is a solid piece, right, that I'm finding the volume of. That's the disk. The washer looks like a disk, except it actually has a hole punched out of it. Okay, so if you've ever pitched washers, you know what a washer looks like. So the washer, to get the washer, basically all you got to do is do 2 discs, and you subtract the middle piece out of the big piece to get that volume of the washer. Okay, so that's the only difference between the dish and the washer. Both have rectangles that are perpendicular to the actual axis that you're revolving about. Okay, so what does this look like? So the 3D picture here of this shape, when we rotate that curve, so the bounded region is actually this region right here. Okay, I'm bounding it below by this y equals 0 because that's the axis I'm rotating about. Okay. This 3D picture kind of looks like a sideways volcano. Okay. So try my best to represent the 3D-ness of this object. You know, not the easiest thing in the world, but not too terribly hard. Okay, so that's a 3D, that's the 3D shape there. Now what I want to do is I want to figure out, okay, what is the volume of one of those discs that belong inside of there. Okay, how do I find that volume? Well, each cross section looks like a little cylinder, right? So how do I find the volume? Well, I need to find the area of the surface and then figure out, multiply that by the width. Now the width here is delta x, okay? So one of those disk volumes is equal to what? Well, volume is equal to capital B times H. So the area of this base here is equal to pi r squared times the height, h. Now, the height happens to be that width, so that's my dx. The pi is still pi, it's just a constant. But what is that radius? How do I get the radius here? How am I going to get that radius r? Well, that's the distance between the axis we're revolving and the curve. So what is the axis we're revolving at some arbitrary x value? That is e to the x minus 0, so it's top minus bottom, e to the x minus 0, so that's e to the x inside my radius. And then remember, I square the radius. So what does this become? It becomes the volume of one of those discs is pi e to the, now power times the power on multiply, so that's e to the 2x. And then my dx, my delta x width there. Okay? Now I want to sum all the discs up. So I want to get all of these discs, not just one of the discs. And so I sum up all of the discs starting here at 0, x equals 0, and I add them up all the way out to x equal 2. So I add up all those discs, those infinitely many discs, between 0 and 2. So how do I write that? The volume is equal to the sum from 0 to 2. That's our way of infinitely adding up all the discs between 0 and 2, right there. Of what? Well, my formula, my area formula is pi e to the 2x dx. Okay? So that gets me the volume whenever I multiply by that dx. So now I just need to integrate. So whenever I integrate this, what do I get? Well, I'm going to use a u substitution. I'm going to say u equals 2x, du equals 2 dx. I only see a dx, so I need to get rid of that 2, so I'm going to divide both sides by 2. So this is going to be 1/2 integral. I'm going to drop my bounds And so I have pi e to the, well, 2x becomes u, okay, du. And so when I integrate, I'm going to pull the pi out front to be a constant. So I'm going to pull that out to be a constant. And the great thing is the integral of e to the u is the easiest one of all. It's just e to the u, okay? And so I originally had it in terms of x. So I'm going to convert this back to be in terms of x. Pi over 2, e to the, and u was 2x. And then my bounds are from 0, x equals 0, to x equal to 2, right? So from 0 to 2. And so I use the fundamental theorem of calculus. Pi over 2, e to the 2 times 2, minus pi over 2, e to the 2 times 0. So this is pi over 2, e to the 4th, minus pi over 2, e to the 0. So e to the 0, if you type that in the calculator, you're just going to get 1. So if you want to factor, you can, and you can factor a pi over 2 out of this, and it's e to the 4 minus 1 times pi over 2 is your answer. And then if you did a decimal approximation, 84.192. Okay? So let's try another one, and we're going to do, instead of a disk, we're going to see if we can't figure out how this washer thing works. Okay, so let's try a washer. Y equals 9 minus x squared, and y equal to 5. Okay, so I'm going to graph this. And it's the same setup. I'm going to rotate about the x-axis. So the x-axis is my the axis that I'm revolving about. All right, so the x-axis here, I'm going to spin about this x-axis. The way I designate that is I do that little loop around with the arrow, and that tells me I'm spinning about the x-axis. Now this graph here, 9 minus x squared, the negative in front of the x squared tells me that I'm sad, so I'm a sad parabola, I'm facing down. The 9 tells me I go up 9 units. So I'm going to go up 9 units. So I mark this so I know where I'm at, 0, 9. And then I'm going to go down like this. And the other thing that I'm going to do, I have y equal to 5. That's a horizontal line at 5. So maybe somewhere around here. Okay. And so this is y equal to 5 here. So that point right there is 0, 5. Okay. Now I need to figure out, where do these things cross? Well, how do I determine where two equations are equal? I set them equal to each other. And so I have y equals 9 minus x squared, and I have y equals 5. So I'm going to replace y with 5 in here. And so that gets me 5 equals 9 minus x squared. If I move the 9 over, I have negative 4 equals negative x squared, so that means x squared equals 4. And so if I square root, I get x is equal to plus or minus 2. So I have a negative 2 here, and I have a positive 2 there. I know that the y value is 5, since it's a horizontal line that goes through, the y value is always 5 there. Okay. So my region bounded is this little region right here. So if you want, you can redraw the 3D version so that you see what it looks like. Okay. Whenever I redraw the 3D version, I'm just thinking artistically, I'm going to draw the original shape. I'm going to put a dot, 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 because it's actually getting spun around, right? So it's hollowed out. So on the outside, looks like this, but on the inside, it's got a hole punched through it. Okay, so I'm going to put the dot dot dots to represent those boundaries around there. It's kind of challenging to envision, but that's the best that I can do. Maybe if you did like a tunnel through the middle kind of thing going on. Okay, something like that. Okay. So, kind of a unique shape. What would one cross section look like here? One cross section, I did a cross section here. Has a thickness. Remember, your cross sections are perpendicular, right? They're perpendicular rectangles to the axis that you're revolving about. So this is perpendicular to the x-axis. Okay. And then the center is torn out. Kind of like that right there. Now, how do we figure this out? Okay, how do we figure out how to get the washer? What I like to do is I like to calculate the big one, and then I like to calculate the little one, and then I subtract the two, and that gets me that one there. Okay, so maybe if I did these in different colors, it would kind of make sense. So I'm going to punch that out of the middle, and then what's left is this right here. All right. So how do I calculate the big one? So the big one, I like to call this a radius with capital R. Okay? Capital R radius. You can call it R1, R2, D2, whatever you want to call it. D kind of sounds like a diameter, but R stands for radius. And I like to call this one little r, so I do a lowercase r. Okay, so I got my big radius and I got my little radius. So how I do this is I figure out, okay, this is pi capital R squared, and then my width, the h. And then I have this one here, which is pi little r squared, and then my width h. And what do? Well, I literally take this and I subtract it out of the middle to get my resulting red washer. And so I'm going to subtract this out just like that. Okay? But what do we know? Well, we know that the width here for this particular problem has a delta x because perpendicular to the x-axis gives me delta x rectangles. So I have pi capital R squared dx, and I have pi capital R, or my lowercase r squared dx here. Okay, and I'm adding them up. I'm adding up all those rectangles from -2, x equal to -2, all the way to x equal to +2. Okay? So I'm going to be adding up all the rectangles from -2 to +2. All right? And each of these have a pi and a dx, right? So I'm going to factor out the pi, and so that leaves me an r squared minus a capital R squared minus lowercase r squared, and then I have my dx. So this is really what I'm end up being left with, okay? So really all it amounts to doing is figuring out what is big R equal to and what is little r equal to. Well, big R is the distance from the center, right, to the outside band, right? So the center to the outside band. Okay, well, what is that distance? Well, that distance happens to be the curve, 9 minus x squared for some arbitrary x value. Okay? So my r here is equal to 9 minus x squared. Now, what about the inside radius here? Okay, what's going on here? Well, for any x value, arbitrary x value I pick, what is the inside radius always going to be? It's always equal to 5. See, that's what that says right there. If you look real close here, anywhere we move this thing, it's always the same radius. So on the inside, that little r there is equal to 5. This big R here, that big radius, is equal to 9 minus x squared. So that one's changing as x changes. But the inside tube that's cut out, I mean, if you look at it and you think about it for a second, what got cut out? It looks like it's a cylinder, a perfect cylinder that got cut out of the middle, right? So that perfect cylinder always has that radius of little r equal to 5. Okay, so that it's not wiggling around any. It has that constant radius there. So this is little r is equal to 5 here. So now we're going to take that information and we're going to plug it in. So I go from -2 to 2 of pi, and then what do I have? Well, I have 9 minus x squared squared minus little r, which is 5 squared, okay? And now all it amounts to doing is simplifying. And if you simplify -2 to 2, I'm going to pull the pi out. I'm going to pull that constant pi out. And so if I square this, let me do some scratch work over here. 9 minus x squared times 9 minus x squared, that's squaring it. That gives me 81 minus, okay, -9x squared and -9x squared makes -18x squared. And then minus and minus make a positive x to the 4th. So this is 81 minus 18x squared plus x to the 4th, and then that's minus 25 dx. And so you can collect like terms here. 81 minus 25. 81 minus 25 is 56, I think. Okay. And so I'm just going to delete this and turn that into 56. Move this over here. And whenever you integrate this, you're going to have pi, and then you're going to have 56x minus x cubed over 3 and 18. Excuse me. And then plus x to the 5th over 5. Negative 2 to 2. Negative 18 and 3 cancel to make negative 6. So I'm going to simplify this. And then you plug in f of b minus f of a, so that f of 2 minus f of negative 2. I'll let you do the algebra on that. And when you do all that nasty math, you get 704 divided by 5 pi, which is approximately 442.336. Okay? So hopefully this kind of helps you understand where the washer method comes from, and then also that easier disk method. Okay? So we'll leave that video at that, and then we'll do some more practice examples just to let you see some different types of problems.